this is Programming Concepts and Methods 1, and we're down to here doing Chapter 6. I think I only have the quizzes up to Chapter 7, so I have to write the rest of these quizzes. I'll try to get them up within a week or so. Anyway, so we'll start with return values and then do a couple demos. So here's the book document for the return values. So I run this bit to get it prepared, and then we can start running these things here. I think I'm going to reload it. Let me just get it so I don't have all the answers hanging out there. It'd be more fun if we start from fresh. So I'll open a tab and then go to the Chapter 6 Jupyter Notebook, which is what we're running here. All right, and run this. All right. So we've used functions like absolute value and round and square root and power, that sort of thing. These are functions that take some numbers and process them and then give you a return value of the result. So we're going to make functions with return values. Now here is square root, for example, the square root of 42 over pi. It's going to calculate it. And here it is spinning up my container. It takes it a few seconds to create the container, essentially a virtual machine I'm running in. And there it is, the square root of 42 over pi. Now, if you'd assign that to a variable, it doesn't print it right away, but you can put it on a line by itself in a Jupyter Notebook. I'm used to just having you say print parentheses radius, which is the way you do it. It'll work anywhere. Anyway, Jupyter Notebooks will sometimes let you just refer to a variable alone and print it, but sometimes they won't. All right, so you can use it as part of an expression, radius plus math square root. That will add these together and create a value, and there it is. And here's a function that returns a value. So you feed in a radius, and it's going to take pi times radius squared and return that. So you define it, and this has no output because it just defines the function. Here we're going to call it on that radius, and we'll get a number 42. So that's what it does. This return value returns it. Notice there's a little bit of error. Floating point values are never perfect. Integers can be perfect, but floating point values always round off to a certain number of places, and you get little errors. So you can assign that to a variable or use it as part of an expression. So here's the area plus 2 times the area squared, and that's going to give you 63. Right, anyway. You can display the value of the variable you assigned it to. It's 42, but you can't access area. If you try to access area, it's going to say area is not defined because area is a local variable in a function, and a local variable here, like area, only exists within this function. And when you're out of this function, it doesn't exist. So that's the thing to realize. This function, the local variable has limited scope. All right, and all right. So also there are functions, if it doesn't have a return statement, it returns none. That's interesting. Here's something that repeats a word by printing it, but it doesn't have a return statement. So if you call the repeat function, it'll repeat that word a few times. But if you take the output of it with the result here, take the result of running the function and put it in a variable, then it will not print it, but it'll print it if you put it here. And the answer, it would print it, but for some reason, Jupyter Notebooks don't like to print none. So if you want to print it, you have to explicitly put in the word print, which is what I always do. That's why I say this thing of just putting a variable online and getting Jupyter Notebooks to print it is for the birds, in my opinion. I explicitly tell it to print, then I know what's going on. And it's going to print the int, which is none. None is a value. That's what's returned by a function that doesn't have a return statement. All right, and so here's one that has a return value. You are going to repeat a string, and so it returns a string that multiplies that word several times. It does not print it. So now, if you call repeat string, it doesn't print it, it just puts it in a variable, and now the variable contains spam, 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 spam. All right. So they call it a pure function because it just does something and returns it. It doesn't print it or have any other effect. All right. So if you didn't have the absolute value, you could define your own absolute value function with x. If x is less than 0, negate it, otherwise return x. That's a perfectly fine way to define an absolute value. Now you could do it wrongly though. You could say if x is less than 0, return minus x. If x is greater than 0, return x. And notice if x is equal to 0, it doesn't do either of those things. and it doesn't have a return statement that it hits then, so it's going to return none for 0, which is not the right answer. So here, it's none, and it's not going to print it, but as we've done before, you could just print it. If I can get in there, print. There. And now we can see that it's none, when it really ought to be 0. All right, so this is a better one. If x less than 0, return minus x, else return x. Otherwise, return something like this is dead code. Now here, if x is less than 0, you return this. Else you return here. Therefore, it never hits this line, because if this condition is, either this condition is true or false, and there's no condition when both of these fail, so you have dead code there. Dead code is a common programming defect where you write code that can never be reached by the logic of your program. So anyway, all right. And here's a good policy, sort of oversimplified example, but I've mentioned before the way to program is only put in a few lines and test it. Put in a few more lines and test it. That way, if it fails, you know where the error is. The number one mistake that beginning programmers do is they write like a whole page of code, and then of course it doesn't work, and now they're lost. They don't know where to find the bugs. So what you do, we're going to try and do this. We're going to take the distance between two xy points in the plane, which is this formula. And so first we're just going to define a distance to read in those values, and it's just going to always return 0. So you define this, and then you test it in distance 1, 2, 4, 6. And it returns 0. It's not the right answer yet, but this shows that at least you got the variables going in there and it's not crashing. So now you try calculate the difference in x, x2 minus x1, and difference in y, print them out, and return 0. So that you make a small step forward and test that to see if it works. And so the x distance between 1 and 4 is 3, and the y distance between 2 and 6 is 4. So that's right. So again, it's not doing the job yet, but it's doing a step in that direction correctly. So now we're going to go all the way. We're going to take d squared is dx squared plus dy squared and print that out. That's going to give us the square of the distance between those points. So now I get the square is 25. And now I can go all the way. I just need to take the square root of that and then print that as a result. So if I do that, now I get the right result, which is 5. I just didn't return it yet. I just printed it. So I'd like to take the last print statement and instead make it a return. And now I get what they call a pure function that doesn't output anything directly. It just returns something to the calling function. And so now if I call that distance, I get the answer 5. So that's the kind of thing you should do. This is a highly oversimplified example, but you should do something simple and make sure it works, add a little bit more and make sure it works. That's the way to keep in control. I always do everything this way. All right, and what you do is with practice, you learn how much code you can write before you start making mistakes. Since I especially when I did a whole lot of reverse engineering Android applications and I was writing Smalley. Smalley is very confusing. And so I learned that I could only change 2 or 3 lines of Smalley before I had to test it because I was likely to have made a mistake. Anyway, so that's the game here. All right, and then there's Boolean functions. You can return a true or a false. That's a Boolean variable. So here it tells you whether x is divisible by y. So 4 is divisible by 2, but 4 is not divisible by 3, not evenly. So it'll tell you if that's true or false. So is 6 divisible by 4? And that's not true, so it's false. Is 6 divisible by 3? It is, so that's true. And so that's a way to go. Now, notice equals equals is the comparison operator. So this will check to see if this is true. Now, you could have, you could also just return that. Here you had an if statement. If it's true, return true, otherwise return false. So you could just return this value, which is true or false, right there. Make your function simpler. That'll return true if it's true and false if it's false. It's simpler. It's less explicit. Like I say, when I first learned to program, I would always do things like this. And when I went into financial work, I actually more often did things like this because I said, in that work, it is not important to be the most efficient and smallest and most beautiful code in that regard. What's important is for it to be the easiest to understand. So everybody can live with it, they can understand it, they can modify it. So sometimes doing things in a more explicit way is better for maintainability and reliability. So you can use Boolean functions here. If is divisible, then print divisible. It's going to be Boolean functions, it will be true or false. Now you might want to say if it equals true, print divisible. And like I say, you can do that and it will work, but it's not really necessary, and it's just a question of style. Like I say, this might be the most clever way. This might be more easy for other programmers to understand and maintain, that kind of thing. All right, and now you can recurse with return values. We talked about recursion before, so here's a factorial. We first need to find a factorial and return 0, so that's not going to be right, but that's a start. Now we add the first part of the definition. If n is 0, return 1, else return 0. So this will work for 0 factorial and 1 factorial, but nothing else. So now we're going to add the rest, where instead of if n is 0, return 1, otherwise take n times the factorial of n minus 1. So this will work. That'll correctly calculate factorials and by doing recursion. And so we can do one of these things where they make a diagram showing it go. And there you go. So it'll be n is 3. You call it factorial of 3. It'll say, well, I need factorial of 2 to do that. I need factorial of 1. I need factorial of 0 to do that. So by function calling itself until there are 4 of it running, it will end up getting the answer. But it's using up a lot of memory and such, running 4 copies of the function. That's recursive functions. All right. And so another one is the Fibonacci function, where you have the first 0, fib of 0 is 0, fib of 1 is 1, and from there on, every future value is equal to the sum of the last 2. So Fibonacci of n is Fibonacci of n minus 1 plus n minus 2. So you can define that here. If n is 0, it's 0. If n is 1, you return 1. Otherwise, call Fibonacci twice for n minus 1 and n minus 2 and add them together. So that should do it. So if I define it here, and then first I'm going to just I'm going to do it up here and get rid of all this. I'm going to print Fibonacci of 3. That'll be fine. I wanted to accept it. When I pressed tab, it didn't take it. I don't quite know how to accept the AI's result. It's the right arrow. So let's see what Fibonacci of 3 looks like, and the answer is 2. That's right. 0 and 1 gives you 1, and 3 is 2. So that's the sort of thing. And Fibonacci of 5 will be some bigger number, and each one of those involves more copies of it running in memory. And at some point, you'll run out of memory, but I think not for a long time. I think we tried this before. 100 is not too many layers deep, although it doubles every time. So 2 to the 100 would definitely be too deep, so I think it's going to run out of memory, the way this is working, where each instance has to call 2 more. Let's see if I can stop it. Yeah, at least it'll let me stop. All right. So in this case, I think maybe even 10 might be as high as you can go. 2 to the 10 is 1,000. Okay, you're able to do that, but somewhere there'll be a limit how many of these copies are on memory. All right. And so, however, if you call 1.5, then it will never finish, and it's going to crash, filling up recursion depth, because the way we wrote it, it never forced these to be integers. And then it goes n minus 1 and n minus 2, and it's only going to stop if it ever gets down to 1 and 0. And since it doesn't, it hits 0.5 and minus 0.5, minus 1.5. It's going to go forever. All right. So you really should add that in. So here's a thing you can do. Is instance 3 this will tell you if 3 is an integer. So it is, but 1.5 is not an integer. So now you can add that in there. If it's not an integer, then don't try it. Say we can only do it for integers. And while you're at it, make sure it's greater than or equal to 0. If it's negative, say you can't do that either and quit. This function will be much stronger than the one we had before. And so now we can do factorial of 1.5, and it will just give us an error message instead of like filling up memory and crashing. And if we call it for the string, it will notice this is not an integer, so that's a good thing. If you call it negative, it'll give you, this is a much better program where you actually handle the errors intelligently instead of having it crash. All right, so we talked about debugging. One thing I do a lot to debug things is just put in a lot of print statements. So here I'm going to do a factor. I'm going to have a space plus times 4 times n, and then have a space factorial. Now, I wonder what the point of these spaces was. Oh, I remember. This is just to indent it. So they're just going to print it out. Okay. They've added some print statements to make it more obvious how the factorial function works. That's all. So now if I do factorial 3, it prints them this way, showing you the layers of iteration. So 3 has to call 2, 1, and 0. And this returns 1, 1, 2, and 6. This shows the function calls, and this is the returns. So it's kind of cute. All right. And so that's all there is there, talking about return values and a few more tips. So let's do a Kahoot. I've got those. I think let me put them in my other browser. All right. This was chapter 6. Just a sec. All right. 923. All right. And I should have folders. There we go. Chapter 6. Good, the number is visible. All right. And there's 6 people online, or maybe 8. So maybe we'll get some players here. And maybe not. Happened to me in my earlier lecture at Los Medanos. There were a lot of online students, but they would not respond. So I'll give it another line or two, and then we'll give up if nobody wants to play. All right, looks like nobody's coming. I'll stop the recording.